This is the existence theorem for ordinary differential equations. So you have this ODE right here, this y prime equals some function of x and y. So y prime is all by itself on the left-hand side, and you could have something nasty on the right-hand side here. And we just call that right-hand side f of x comma y. And this is an initial value problem, so we have y at some x naught equals y naught. Here I've drawn a little, here let me put in the x and y. Some little, point, x naught, y naught. This one happens to be in the first quadrant. And we also have this rectangle that I've drawn. It's an open rectangle, meaning it doesn't include the boundary. That's why it's a dashed line. And this x naught, y naught is within that open rectangle. So here we have our implication statement. F of x, y is continuous on the open rectangle R. So, everywhere in this open rectangle, this function f of x comma y, which y prime equals, is continuous. Then the initial value problem has at least one solution within R, and it goes through this, point here. And so this statement is actually fairly weak. So first, you're guaranteed there's at least one solution, and there can actually be, infinitely many solutions is one possibility. So you could have one, or you could have more than one, but you at least know there is a solution, so something is going to go through this point. The other thing is you have this open rectangle R. It doesn't mean that it's going to span the entire rectangle. So something that could happen is, I have my point, I have my rectangle. Let me do my dashed line again. Okay, and I might have a solution, that works fine when I'm nearby, but it goes to a vertical asymptote pretty quickly. And so that might happen. Or it might be very well behaved and it exists in the entire region, and maybe there's a problem once you try to pass through it or get out of it. But that's a possibility. And another thing, if this statement isn't true, so that's the other one. So f of x and y is continuous in the open rectangle, you at least have some sort of solution around your initial condition x naught, y naught. It might not work once you get further and further away, and it might not even work while you're inside the open rectangle, but you for sure have at least something that is close by to x naught, y naught. You don't know how close that is. It doesn't mean it's, the closeness doesn't have to do with R. You just know there's something, some unique, a solution exists. There also could be, an infinite number of solutions. So one option is one of the differential equations we'll solve actually has an infinite number of lines leading to one point, then it comes out with an infinite number of lines. And so there's actually this kind of non-unique solution, it looks like, to the differential equation. And there's lots of things like that. So just keep that in mind. F of x, y is continuous on the open rectangle R. Then the initial value problem has at least one solution within R. So there might be infinite solutions. There might be, exactly one solution. You don't know. And then it's not guaranteed to exist, for the entire time within R. You might get to the boundary and you might pass through it and you're fine. You might, get to the boundary and there's a problem, or you might have a problem before you even get to the boundary, like a discontinuity. So that's it. So, just keep that in mind. This is an implication. So you don't know a whole lot, even if f of x, y is continuous. All you're guaranteed is that if you have your point and it's in your rectangle, you have at least a nice solution nearby the point. That's all you know.